Hey everyone, welcome back for more calculus and logistic growth. This time we're going to be doing basically the home version of what would normally be a really fun activity to do in class. Unfortunately, we don't have a full class of people here to play around with, so I'm going to have to fake a little bit about what we're going to see. So let's get started with logistic growth. Now we're really going to get into actual logistic growth. So here we go with Hufflepuff House. And Hufflepuff, this tells you a little bit about this, the Hufflepuff House. And while on winter vacation, you and some puffers, every student currently in class, need to stay in the dormitory instead of going home. And the prefect decides that on the 10 evenings of vacation, each puffer needs to have dinner with a different puffer that night. I just like saying puffer. So the dinners are one-to-one, and you can't have this dinner with the same student twice. So this is kind of what we would fill out in class. So night one, if I was, I think we're pretending that I'm Cedric Diggory here. I'm going to have dinner with Tasmeen Appleby. Night two with Patrick Bagby, etc., etc. Night 9 with Anthony Rickett. And that's great. But unbeknownst to you and the rest of Hufflepuff House, one of the puffers, and in this case me, Cedric Diggory, is going to contract dragonpox. So every time I have dinner with somebody, I'm going to give them dragonpox. And every time that person has dinner with somebody, they're going to get dragonpox too. So as we can see, very quickly, exponentially, the number of people with dragonpox is going to start increasing. But there's only 31 people in the tower. So we can't ever infect more than 32 people. Now here I've gone ahead and I've traced, with my sample classroom, how many people would be infected with dragonpox based on who they had dinner with. And we've got on the first night 0, only Cedric. Night 1, Cedric and who is this? Tasmeen. Cedric and Tasmeen now both have dragonpox. Night 2, there's going to be 4 people with dragonpox, etc., etc. And eventually, we start to have 31 people infected with dragonpox, which is all of the Hufflepuffers. So if I graph these, the night versus the number of infected Hufflepuff, we get this curve right here. Okay, and I don't know if you can see it, so I'll try to trace along with it. This best fit curve might look like this if I were to figure out a line of best fit. And that S-shaped curve is called a sigmoid. It is a curve for what we call the logistic growth function. And the logistic growth function is the function that we use whenever we have some kind of an exponential growth and a carrying capacity. There is a limit to how many people can contract dragonpox because only 31 Hufflepuff people are in the house. So the 31 people in the house, as you notice these last 2 points right here, are both 31. And as it approaches that 31, notice how it kind of displays, what's the word for this? Oh yes, a horizontal asymptote. So let's draw in that horizontal asymptote. So that horizontal asymptote right here, we're going to call this the carrying capacity. Because that's how many people, that's the maximum number of people that can be infected with dragonpox. And the variable, or the parameter that we use for the carrying capacity is M, capital M. So let's take a look at this, verifying our answers. As t goes to infinity, what is the population going to approach? Okay, if this is the population on the horizontal axis, it looks like we're going to approach the carrying capacity. And that should make sense. As time increases, the number of people infected are going to approach the carrying capacity, which in this case is 31. And finally, when is P prime going to be the greatest? When is the dragon pox increasing the greatest? And it seems like it's increasing the greatest right about here, wouldn't you say? Right around 4.5-ish. Around T is approximately equal to 4.5. And what is at 4.5? It looks like the population, the number of people with dragonpox, is about, I don't know, 17. When population is about equal to 17. And this is a very important point that we're going to make. So looking here at what a logistic growth curve really is. First of all, it follows this differential equation. You have to memorize this. Okay. Notice that it is a joint proportion. So the joint proportion with the growth, the rate of growth, is proportional to jointly the current population and the, and I put the word room here, but basically how much more can this disease grow? What's the carrying capacity minus the current population? So it's jointly proportional to however many people currently have dragonpox and how many people don't have dragonpox. So properties. We start off with a growth at exponential rate. And as the rate of the population increases, the rate that the population increases, which is dp dt, is going to be a maximum when p is equal to 1/2 m. In other words, max p prime when p equals 1/2 m. Okay. As the population approaches m, in other words, as t approaches infinity, the population, the number of people infected, is going to approach the carrying capacity, which all should make sense. Today, we're just looking at this logistic growth equation just on, its properties, not so much with the calculus. We're going to save that for the next time we meet. So we're going to take a look at this, and gosh, this does not look like, let's compare this. Let's compare that with Kp m minus p. We'll compare that with what we currently are looking at. 144p minus 0.12p squared. Okay, they don't look like they're the same, although if you are paying attention to your algebra, you can see some things you can do here to make these two look the same. I should read the problem, actually. I got a little bit excited. The number of caribou in a certain herd follows this differential equation. Okay. Is this logistic? First of all, we should ask that. And let's try and make this look like the logistic equation. The first thing I'm going to do is, this is p times m minus p. This is p minus p squared. So the minus sign looks pretty good. But I'm going to factor out p, so that might help this look more like the differential equation. P multiplied by 144 minus 0.12p. Okay, so that's a nice factoring. Now, over here, the coefficient of p is 1, so I got to factor out that 0.12. So if I factor out that 0.12, that's going to give me 0.12p here. And inside the parenthesis, we're going to get 1200 minus p. Now take a look at these two. K is equal to 0.12. M is equal to 1200. Now we can answer some questions. Part A. What's the carrying capacity? So carrying capacity is equal to M, which is equal to 1200. And we only got that through factoring. See, no calculus quite yet. And part B, how many caribou are in the herd when the population is growing the fastest? Population is growing the fastest. That means max P prime. And that occurs when P equals half of M, which is equal to 600 caribou. Okay, and we should write a summary sentence for that. So the herd is growing the fastest when there are 600 caribou. Let's take a look at some important ideas. Now, like the exponential growth and decay equations that we looked at earlier, logistic growth is one of those well-known differential equations, which should signal to you that you don't actually have to do integration always for this kind of equation. It models growth under a carrying capacity. Of course, growth begins at an exponential rate because there's nothing stopping or inhibiting growth. And as the growth or as the population increases, the P prime, the rate that population increases, will be a maximum when P is half of the carrying capacity. And as T goes to infinity, the population approaches the carrying capacity. All of those should make sense on an intuitive level. We've done literally no calculus today, so I don't see why this would be too difficult, I don't think. It does boggle the mind sometimes, though. Let's take a look at Check Your Understanding. Hufflepuff House maintains a clan of badgers. Apparently a group of badgers is called a clan. Look it up. That's a house animal for Hufflepuff. So when there are 14 badgers, the clan is growing at its fastest rate, 5.88 badgers per year. So what is the differential equation? Now there's not a lot to go on here. We do know that the population, or we assume that the population, is going to be logistic. So that leads us to knowing that the population, dp dt, the rate of growth, is going to be kp m minus p. But that's all we know right now. Well, the population grows fastest when there are 14 badgers. So 14 should be half of the carrying capacity, which means that the carrying capacity is equal to 28. Let's substitute that in there. dp dt is equal to k p 28 minus p. And for the last thing, when the population is growing fastest, when p equals 14, dp dt is equal to 5.88 badgers per year. Now we have stuff to substitute, even more stuff. We didn't even think that we had this many numbers to substitute. So dp dt is k multiplied by 14 again, that's equal to 5.88. Doing some algebra, we get k is equal to 0.03. So now I think we're ready to answer part A. So part A, what is the differential equation? dp dt, that's equal to k, 0.03, multiplied by p, multiplied by m, 28, minus p. So there's my differential equation. Now, for part B, when there are 10 badgers, what is the growth rate of the clan? So basically they're asking, what is p prime of 10? Well, that's dp dt evaluated when p equals 10. Oh, I'm sorry. P prime, we don't know. We don't know when what t that occurs. But we have a differential equation for the population that is only in terms of P. So this should do it right here. 0.03 multiplied by the current population, 10, multiplied by 28 minus 10. How many... Okay, this is an infection, but how many more badgers can we have in the clan? And we get 5.4. Or, when there are 10 badgers, the population is growing at a rate of 5.4 badgers per year. Now, this logistic equation stuff, as you saw, we didn't have to do any integration. We didn't have to do any differentiation. But we did have to know a lot about the behavior of the logistic growth curve. And that's typically what you're going to see on an AP test. Not so much the integration of a logistic growth equation, but recognizing the logistic growth equation, knowing the properties of the logistic growth equation, and feeling comfortable with it, really. So that's it for today. We'll see you next time when we actually do some integration for the logistic growth equation.